Okay, welcome everybody to today's seminar of the joint seminar series of the ICMM and the IFIMAC in Madrid. It's a pleasure to welcome Enrique Burzurí from the IMDEA, also on our campus, who will give the seminar today. To introduce Enrique briefly, Enrique studied physics in Zaragoza and finished with the master in 2007. Then he continued there in the group of Fernando Luis doing his PhD, which he finished in 2011, where he was working mainly on molecular magnets. Then he spent a postdoc in Delft working on molecular electronics with Harry van der Zandt. And finally, in 2017, he came back to Spain, to IMDEA. And since 2018, he's a tenure-track researcher there. He's mainly working on, as I said, molecular magnetism, low-dimensional materials, also nanotubes, and especially he's focusing on quantum properties, and this will also be part of the talk today, where he will speak about molecule-based magnetic heterostructures for spintronics and quantum computing. So welcome, Enrique, and please start.
Okay, so thank you, Sigmund, for these kind of introductions. Thanks also to the organizers for this chance to show my research here today in this nice initiative of the IFIMAC and the ICMM meetings. So indeed, I'm going to talk today about molecule-based magnetic heterostructures for spintronics and quantum computing. So please, if you have any question at any point, or if you cannot hear me properly, just let me know, okay? So before going to the science, first let me show you a bit my group and the lab. The group is actually quite tiny. It's just myself and these two PhD students, Lucia and Aise, that have done most of the work that I will show you in the next slides. My lab, as Sigmund says, is in the nanoscience, in particular in this corner of the building, and it is in essence an electron transport laboratory. And for that, we have all kinds of electrical probe stations to measure in different atmospheres, gas, vacuum, low temperatures. We have a cryo-free cooler that we are setting up to try to measure in the microwave regime, and we have all kinds of also 2D transfer stations to work with 2D materials. Okay, so then the molecules for me can be think of to be part of this bigger family that could be the low-dimensional materials, that in general, all those that are not 3D. For example, we could have the 2D materials like graphene, that is very well known, 1D materials like the carbon nanotubes, also very well known, and then the smallest dimension possible here that could be the molecule itself, the 0D. Of all these materials, I'm particularly interested in those that are magnetic. So those that present a spin and some other magnetic properties that we can use, for example, to process information, as I will show you later. And if you remember, in the title of my talk, I was particularly talking about molecule-based heterostructures. So today I would like to show you how we can combine these magnetic molecules with other low-dimensional materials to create kind of heterostructures that are very useful for fields like spintronics and quantum computation. So the molecule, the magnetic part of the molecule, will still be the core of the physics and the applications that we want to have, but you will see how in combination with, in particular, carbon nanotubes, we can have certain advantages. So my talk will be focused precisely on this combination, but before going to that, let me first show you why we think that this could be very interesting for quantum computation. Okay, I don't really know your background, so just to refresh a bit, what is quantum computing? Okay, this question may lead us a bit to this other question of what is a quantum bit. So a quantum bit is just the quantum analog of the classical bit, where instead of having the information encoded into levels like up or down or 1 or 0, in the quantum bit, what we have is actually the quantum superposition of these two states in such a way that now our bits are not 1 or 0, or this arrow pointing up or down, but would be this arrow pointing in any direction of this spherical representation, and our state would be now a linear combination of these two states. The properties that a physical system need to have to encode one of these qubits would be basically to have two-level systems with a certain energy spacing like this one, and also to have a certain coherence time, a long coherence time, so that this superposition between these two states is alive long enough to do operations with this quantum bit. The criteria to have a good qubit is actually summarized by this DiVincenzo criteria. So the qubits need to be scalable, so we need to be able to fabricate several in an easy way and that are identical, reproducible. Also, we need long coherence times to create, to do a number of operations before the superposition decays. We need to be able to initialize this qubit in a specific orientation or in a specific state. We need to interconnect qubits and do operations with logic gates. And finally, of course, we need to be able to measure this qubit. There are actually already many physical systems that can be used to encode one of these qubits. Maybe the most famous ones that most of the companies now are following would be the superconducting qubits that most of the people know. But I would like to show you today how spin qubits, and in particular molecular spin qubits, could also be alternative or also very good candidates that present some advantages, of course also some disadvantages, but some advantages that superconducting qubits may not have. These are just some examples, but actually there are many others, like electrical dipole qubits, trapped ions, and some others more exotic, even like topological photons or plasmas. Okay, so why molecules and why magnetic molecules? So the first advantage for me is the reproducibility. Molecules are synthesized by a bottom-up approach in chemistry, so that we can fabricate thousands of these molecules that are identical to each other, what is very important for qubits. But also the qubit itself, that could be encoding the spin in the center of the molecule, can be protected by very big organic shells that protect the qubit from the outer world, so protects from the coherence of this quantum bit. The nice thing of chemistry actually is also that chemists, well, I'm a physicist, but chemists can tune these molecules. They can, for example, modify these organic shells, but also they can change the metal or the rare earth that gives the spin to really fine-tune the properties of the qubit. For example, to change the coherence time, to improve it, to change the magnetic spectrum between the levels, and something that will be very relevant, the number of spins that we can have in a molecule. That's why there are actually many groups now that are trying to synthesize different models or different molecules that could act as molecular spin qubits. For example, some would be the radicals, the famous single molecule magnets, single ion magnets based on rare earth. And the idea in the end is to try to maximize the coherence time of these qubits so that we can do operations with them. We are getting close to the millisecond, what is actually not that bad at all. If you remember, also I told you that it's interesting that we can put more than one spin in the same molecule. So this leads us to the nice property of scalability. By choosing a proper combination of metals or rare earths and a proper geometry, what we can have is, in the end, is a very complex magnetic spectrum of these molecules that in the end allow us to encode in a single molecule, for example, in this case, several qubits or even qubits. And in this other case, we could, for example, encode a quantum gate in a single molecule. So this is really scalable. So we don't need huge architectures to interconnect qubits to each other. So this would be our system, and why we think magnetic molecules could be interesting for qubits. Now we need a hardware. We need a way to read and to control, to modify this quantum state or this spin state in these molecules. The way that typically is done now, also with superconducting qubits, would be based on the physics of cavity quantum electrodynamics. So just to show you a bit the basic idea, we would have our molecule here that could have these two states, the two states of the qubit, and it could be in between two mirrors that are trapping a photon that would be given by these energy levels. Okay, so we would like to address the spin state with a single photon. The idea is now that, of course, we have these two systems, but there is also a certain coupling term between them. So if this G value, that is the spin photon coupling, is strong enough between our spin and our photon, now we don't have two independent systems anymore, but we can have kind of a hybrid system where all the levels are kind of related, interconnected. If the G is strong enough, meaning that is larger than the decoherence time, we can have that the transmission will actually tell us what is the state of our quantum bit. So by measuring the transmission across this mirror, we should be able to see the quantum state of our molecule. This would be a bit the idea, the physics, but of course we want to translate this to a solid state device or something that we can actually use. So now the photon, instead of being trapped in between those mirrors, what we do is to trap it in a superconducting resonator. That would be something like this. This would be schematics. This would be the device itself that we have fabricated. Okay. The idea would be to have this central transmission line separated by these two capacitive couplings, and then our photon is trapped in this central part. The frequency of the photon depends on the length of this line, and just to give you an idea, we typically work now with photons below the 10 gigahertz. So in the end, in the microwave regime. So this would be our device. This would be a real image of one of them. Now we want to put our molecules in here to try to address this qubit. And now is where the problems come, actually, because one of the disadvantages that molecules have is that the spin photon coupling is relatively low for these molecules. The spins are magnetic entities, right? So they actually couple to the magnetic component of the photon. That is maximum in the central part of this transmission line, so somewhere around here and on the edge. What people are doing, for example, Fernando Ruiz in the ICMA in Zaragoza, to try to get this strong spin photon coupling, is to increase the number of spins, because then you see you can increase the G. But this is not something that we want to do in the long term, because what we actually want to do is to couple a single photon to a single molecule, so to really use the spin of a single molecule to encode information, to encode a qubit. So if you see this formula, basically the other way that we can do, or that we can use to increase this G, would be to increase the magnetic field in this case. Okay, so the magnetic field can be increased, of the photon could be increased in two different ways. One will be to increase the frequency. This is not something that we want to do, because then we go to a different scale of energies in our device, and also we should decrease by a lot the dimension of our device. So the only other alternative could be to actually decrease the width of the central line. Okay, so this R would be this width of the central line. Also, Fernando in Zaragoza, he has already done some calculations, and they see that indeed by picking these three model qubits, they see how the spin photon coupling increases orders of magnitude by decreasing orders of magnitudes the width of this constriction. The problem here comes that when you multiply this by the coherence time of the qubit of the spin of what they see is that only this one would be above 1 in here. So this product has to be above 1 to really have a strong spin photon coupling, and all the others would be below, and even this would be above only for very, very narrow widths of this nanoconstriction. So we are really hitting the limit of conventional nanofabrication techniques to have these constrictions that may allow us to have this strong spin photon coupling. These things can become even worse, because it not only depends on the width of the central line, it also depends on the height. So on how far our molecule is, so I'm sorry, I just realized that I have questions in the chat. I don't know if you prefer me to answer them now, or just let me know, okay? Yeah, so you have also to increase you have to take into account also the distance between the molecule and the central line, okay? Because the farther is the molecule, you will see that at some point, if you continue decreasing the width, this saturates and you don't get any more an improvement of the spin photon coupling. Okay.
Enrique?
Yeah.
I allow the question.
Yeah, sure, please.
Hi. Yeah, sorry. I was wondering that when you say you can reduce the width and hence increase the coupling, are you keeping the current constant or the current density remains constant?
The current is kept constant. What then gets increased here would be the current density.
Okay, so basically the mechanism is you are increasing by reducing the width, you are able to increase the current density in the system.
Yeah, exactly. Yeah, that would be a bit the idea in practice.
Thank you.
Yeah. Thank you for your question. Yeah, indeed, that would be actually the idea. Okay, that would be the idea a bit of reducing a bit this line. Okay, so then I think you can see a bit what is the goal and what is the nice idea that Fernando was trying, but you can see the limitations because of the qubits and also because it is not easy to really put a molecule in a specific position with a specific height. This is not something that is easy to do. So what we are trying, I cannot change the slide now. I don't know why. No. So what we are actually trying to do now in my lab at INDEA actually is now to try to go to even smaller scales and try to replace part of the transmission line by a single carbon nanotube. So we literally cut the transmission line at a specific position and we deposit a carbon nanotube. What is the idea here is that the carbon nanotube by itself is already extremely narrow. So in the end, is a 1D material. So we can have carbon nanotubes that are around the 1 nanometer. So we would be really on the left, you know, on this limit part here of the graph. But the carbon nanotube has an extra advantage, and this advantage is that it's very easy to functionalize with molecules, and in our case with magnetic molecules. So we would be optimizing not only the width, but also the height. It would be minimum, we should try to do it minimum. The additional advantage is that when we want to work with individual molecules, it's really complicated to place an individual molecule in a very specific place of a device. So with the carbon nanotube, we could use it as a vessel to really locate the molecule in specific places. Okay, so, well, this is how we actually fabricate our devices. These are done in the clean room facilities at INDEA in collaboration with Alicia and Marina. So the idea is to start with a silicon oxide substrate where we spatter niobium as a superconducting material for our device. And then by a series of steps with optical lithography, we are able to define our device, and by etching, we can have the final device that you can see here. So this would be a real image of one of the devices. So you see that for now, the gap is quite big, let's say, so it's 500 nanometers, but we can do it smaller if we use electron beam lithography, or also we have been trying with FIB to really make very, very small gaps to contact our tubes. Of course, we need to put the carbon nanotube, and we cannot just rely on leaving the nanotubes on the surface. So what we do is to use de-electrophoresis. So what we do is to put a drop of a solvent, in this case isopropanol, containing the carbon nanotubes already dispersed. And then we apply an AC bias between these two tips of our central transmission line. The AC field is kind of creating a dipole in the carbon nanotube that gets attracted into the central part of the gap where the electrical field is the largest, and also the gradient of the electrical field. That it is what we need actually for the electrophoretic force. Okay, so this would be a bit the process of how we do it. We really have low concentrations of carbon nanotubes in the solvent because we need just one. We would put a drop on top of our device, and finally, you see, we would be able to get a single carbon nanotube in the central part of our transmission line. This would, for example, with gold electrodes, just to show you that we can actually do this in all kind of nano-fabricated devices. The first thing we have done now, this is relatively recent, okay, so what we have done now is to characterize this new device at room temperature. And what we see is that after the electrophoresis, indeed, we have been able to breach this central gap that we have done in the superconducting device. Those are the good news. The not so good news is that the contact resistance between the carbon nanotube and the superconductor is relatively high. This is, of course, something not good for the quality factor of our resonator. So we are trying to improve this, for example, by doing some thermal annealing. We see that by heating the sample up, we can get more than 1 order of magnitude improvement on the current on the device. And we are also now trying to actually cap our niobium with palladium that has a closer work function to the carbon nanotube. So we would expect to have even better coupling between the nanotube and the superconductor. Of course, the next step would be to even create smaller gaps in our central line. Still, we thought that would be nice to do all the measurements already in this kind of devices. So we have measured, this has been done by Alicia in the Centro de Astrobiología. We have measured transmission in the microwave range in our device to see what happens. So this would be the open circuit. We have all kind of peaks here that are coming most likely from parallel paths or the background. But we see that as soon as we put our carbon nanotube in the circuit, we get this extra peak in the transmission, and from the frequency, it could fit more or less with the length of our resonator. So it looks like, of course, we need to improve a lot of these devices, but they are potentially going to work for the molecules that we want to put. Okay, so this would be a bit the idea, why the molecules, why we use these superconducting devices, why the carbon nanotube. And now, as I said, we need to put some magnetic molecules that are suitable for this purpose, and we need to functionalize the carbon nanotube with specific functionalization methods. I'm saying this because we are not using conventional functionalization techniques for the carbon nanotubes. With conventional, I mean, for example, van der Waals interactions, because those are rather weak and you cannot control them very well. Also, we don't want to use covalent bonding, because covalent bonds between molecules and nanotubes would actually damage the carbon nanotube, could create local spins in the nanotube. So in the end, they would degrade the carbon nanotube lattice. This is something that we don't want. So then what we are actually using is this endohedral encapsulation of magnetic molecules. So we actually put the molecules inside the nanotube. We are also using this mechanical interlocked bond developed by Emilio Perez at IMDEA Nanoscience. Okay, so basically now the molecule is not inside, it's outside, but embracing the carbon nanotube. So it's a very strong bond, but it's not really making covalent bonds to the nanotube. And finally, if I have time, I will show you how we want also to implement spins in this kind of devices with other kinds of materials, for instance, intrinsically magnetic to the materials or heterostructures. Okay, so I will start with this one, with the mechanically interlocked molecule that we call MINT. So the basic idea of the molecule would be this one. So this is a linear molecule we call that contains two magnetic porphyrins. The metals would be here, could be either cobalt or copper, and in any case, both metals are giving us two spin 1/2s in the molecule. So what in the group of Emilio, Sarah have been able to do is actually to close this linear molecule into a ring like this by closing these bonds. And if you have the nanotubes there, of course, it's not that easy, but I don't really know the details. But if you have the nanotubes there, you can embrace this ring around the carbon nanotube in such a way that indeed this is a much stronger bond than the van der Waals. You keep the spins in very close proximity to the wall of the nanotube, and at the same time you are not disturbing this wall of the nanotube. Okay, so we have done some DFT modeling of this molecule, and we see that is very important for us, at least in theory. What we see is that the plane containing the metal, the one that is giving us the spin, is not distorted when we embrace this molecule around the nanotube. And also you see that the metal is really, really close to the wall of the carbon nanotube. Okay, so once we have the molecules, we have characterized the structure of the final system to see if indeed we have what we think we have. The initial more rough characterization is thermogravimetric analysis. Okay, so in this basically we burn the sample and we measure how much mass we are losing. The black would be just carbon nanotubes without the molecules. So you see that the carbon nanotube burns at around 500 something Celsius. And now we have the mints containing the cobalt and the copper porphyrins. We see an extra peak somewhere here that is coming from the molecules. And we see that the drop corresponding to the burning of the nanotube is moving towards lower temperatures. This is happening basically because of the presence of the molecules in the tube. The metals that are present in the porphyrins in these high temperatures tend to catalyze some reactions in the tube, making it to burn at lower temperatures. Also, if you see, we have a remaining mass here that does not burn, that precisely are the metals in our porphyrins. Okay, so this is already a good indication. We have done also some high-resolution TEM images of some of these tubes, and in some of them, we are very lucky to see this nice image where we see the carbon nanotube with the microcycle with the two porphyrins around the tube. And if you measure these dimensions, it fits very well with what we expect from DFT for the dimensions of the molecule. I have to highlight that it's not really easy to get this kind of images because the electron beam tends to immediately almost destroy all the organic part of our molecules when we put them under the electron beam. We have then also some AFM characterization of our nanotubes, and we see that only those that have been functionalized, they present this kind of spots in here that if you measure the height, they fit quite well with the fact that we have the molecule embracing the nanotube. We wanted to see actually what was happening to the metals or to the geometry around the metals when they are first in the monomer, then in the linear molecule, and then embracing the carbon nanotube. So what we have done as well is X-ray absorption near rates spectroscopy. I will not go into detail, but just to show you that we have done it in all the derivatives from the monomer to the mint. And what we basically see in the cobalt and in the copper derivatives is that there are not big changes in the molecules when you go from the monomer to the mint. The first important thing is that the cobalt and the copper are still there in the porphyrins when they are in the mint, that they are still 4 coordinated to the molecule, to the nitrogens around in the molecule, and that they are in the +2 oxidation state. So we don't really see heavily distorted molecules in the nanotube. We don't see oxidation, reduction of the molecule. So this is very important for us for the purposes that we want to have. Now we of course are interested in the magnetic core, in the magnetic part of these molecules. So what we have done as well is EPR on all these molecules. This would be the EPR spectrum of spectra of the cobalt porphyrins for the monomer, this linear dimer, and the microcycle in here, and this would be the corresponding ones for the copper porphyrins. Okay, so the first thing we see, and that is common to all the cases, is that there are no big changes when we go from the monomer to the microcycle. This again is consistent with the XFs, with the X-ray absorption spectroscopy. Okay, only tiny variations in the fine structure can be seen. This is one important conclusion. The other one would be that since they are very similar, this is also telling us that magnetically these two metal centers are not coupled, so they should be independent in principle. And the spectra can be very well fit with spin 1/2 in both cases. So this is very important for us. There are though some differences between the spectra that are also interesting, is that in this one, in order to fit the spectra, you see that the spin is not really located on the plane of the cobalt porphyrin. Okay, so actually it's a bit displaced over the transversal axis of the porphyrin. This has been seen before for cobalt porphyrins. In contrast, in these copper porphyrins, we find, if we fit the spectrum, that actually the spin is really in the plane of the in this case, copper porphyrin. Okay, so we actually can see this very well because in this case we do see all this structure that is coming from the what is called the super hyperfine interaction, due to the interaction between the spin of the copper and the nuclear spin of the nitrogen. Whereas here we don't really see it, and precisely because it's a bit out of the plane of the porphyrin. Okay, so what happens now when we do the EPR of these heterostructures or these hybrids, if you want? So this would be the EPR of the copper porphyrin mint. So what we see is a high resonance that actually corresponds to spins in the carbon nanotube. Okay, so this would be either itinerant spins in the carbon nanotube, or maybe localized spins due to impurities or defects on the carbon nanotube lattice. The good part for us is that on top of that resonance, we can actually see the magnetic spectra of the copper microcycle. So we are actually seeing the molecules on the carbon nanotube. Also interesting is that the spectrum does not basically change. So it's almost the same, only some of the peaks look like start to split. We think that this is just because some molecules are slightly distorted, or because the two porphyrins are not exactly equivalent with respect to the carbon nanotube. Okay, so this in principle is good news. The different thing is when we measure the cobalt porphyrin mint. Okay, in this case we see again this strong resonance coming from the carbon nanotube, but actually we are not able to see any sign of the cobalt. This is actually very strange because we know from EXAFs that cobalt is there, but we think that either something has happened here to the cobalt, or just the functionalization is a bit lower, so the sign is buried in this part here, or maybe it's related to this difference in between the position of the spin in the molecule. The fact is that we don't really see it in cobalt. And of course, this is not a single measurement, it's by several trials and several syntheses of these molecules. Okay, so in the end, looks like this is the best candidate that we can use for our measurements. So what's next? This should be done already, but the last year was not easy for us, as you can imagine. So now the idea is to actually measure spin echo experiments that will allow us to measure the coherence time of this molecule. We didn't do it yet, but we are quite optimistic because a very, very recent report has shown that in a similar system, so porphyrins on a surface, you can have coherence times of around microseconds, what is not so bad. And of course, then the final idea would be to put them, these hybrids now in our superconducting transmission lines and see how these peaks now behave in the presence of these molecules. Okay. So, well, with this, I would finish this part here. And then I would like to go to this second part of the talk, where I would like to discuss this endohedral encapsulation of magnetic molecules. Okay, in particular, the molecules that we have selected are these spin crossover molecules. For those of you that don't know, these molecules have the ability to change their magnetism, their spin, under an external stimulus. For example, in this case, they can go from a spin 2 to a spin 0 by modifying slightly the local geometry around the magnetic part. That in this case is an ion. In the case of the molecules that we are studying, for example, this is done with temperature, and we can go from high spin 2 to a low spin 0 at around 160 Kelvin, starting at around 175. Okay. Well, this magnetic part has accompanied other kind of changes. For example, the molecule or the crystals of the molecules change their color, and also we know, and this is more relevant for us, as you will see, that the molecules change the volume. So they are bigger when they are in a high spin state than when they are in a low spin state. These molecules are maybe not the best candidates for quantum computation, okay, but they are going to be very interesting for us for Spintronics purposes, as you will see. And the encapsulation process will help us to do it with other magnetic molecules, maybe more suitable as qubits. Why? Well, you know that having this kind of spin changes is very interesting for Spintronics. The problem people have faced when trying to use these spin crossover molecules is that actually they are quite insulating materials. So they have tried, for example, these people have tried to measure conductance across crystals, and they do see conductance, but it's very low, it's very difficult. And that's why many groups have tried to integrate these molecules in other devices. For example, Julian in Delft with Gerre van der Sand tried to put them on top of graphene. Other people have tried to create composites with other more conducting materials. Myself, I tried to measure conductance directly across the single molecule. So based on the previous idea I was discussing, we were wondering what could happen if we put now the molecules inside the tube. So we use the nanotube as a mechanical backbone, but also as an electrical backbone to detect these spin changes in the molecule. Okay, so the way they are encapsulated is the following. So we start with closed carbon nanotubes that are commercial. We do kind of a thermal annealing. So we burn part of the tube to open the two parts of the two extremes of the carbon nanotube. And then basically we put them all together in a closed vial, and we sublimate the molecules so that the molecules tend to go inside the carbon nanotube. This would be a bit the final material that we would have. The first tool we have to check this encapsulation is again the TGA, the thermogravimetric analysis. As before, here you see the burning. The black line would be the burning of the carbon nanotube. The purple one would be the burning of just the molecules without the carbon nanotube. And the hybrid material in here, you can see that the peak of the molecule shifts to higher temperatures. We think this is because the molecule is protected inside the nanotube. And you see how, as before, this nanotube burns at lower temperatures. And again, we have the residue of the iron residue of the molecules. We have done also some STM and yields analysis of our materials. And here you can see a carbon nanotube, and you see that it's actually filled with stuff, let's say. And in some parts, you see these bright areas. These bright areas are actually corresponding to higher or high atomic numbers. And if you do some yields on this area, you see how indeed they correspond to the presence of iron inside the nanotube. I have to highlight again that we couldn't get a nice image of the organic part of the spin crossover, and we think it's just because we just destroy it when we expose it to the electron beam of the TEM. Okay, so all this part would be most likely the remanent iron atoms of the molecule. Okay, so to try to see the molecule as a whole, we have done some Raman spectroscopy of these materials. And just briefly, we basically see these large peaks corresponding to the single carbon nanotube. And in some lucky spots, we are able here, this green part, to see the contribution of the molecule to the Raman. Something we see, if we study now in detail all these peaks, is that the carbon nanotube peaks, all of them are blue shifted. So they move to higher energies. This would be, for example, the position of the peaks just for the nanotube, and this for the encapsulated derivatives. This blue shift has been described before when you have a molecule that is giving you certain charge transfer to your carbon nanotube. Could be also due to aggregation, but also interestingly could be due to mechanical strain. So the fact that by putting the molecules inside the tube, you are putting some strain on the carbon nanotube. We have as well tried to see if we could track the spin crossover in the Raman, but it was not so easy. But still, we were focusing on some of the peaks of the molecule, and we were using this peak as a reference, what we could see, but now measuring the height, so the intensity, as a function of the temperature, is that some of the peaks decrease their intensity at precisely the temperature of the spin crossover. This one around 160 to 175. It's interesting to see that in the bulk, so in crystals of the molecules, this happens at slightly lower temperatures than what we see in the molecules encapsulated in the carbon nanotubes. Okay. Now, so we have these indications that the molecules are there, that the spin crossover most likely is preserved in the molecules or in some of the molecules. Now we really want to do spintronics, or at least to integrate it in electronic devices. So using very similar techniques that I showed you before, we fabricate these nanoscale devices, where in this central part here, we have several electrodes separated by a few hundreds of nanometers, okay? So then in here, using again the electrophoresis as before, we are able to put this individual carbon nanotube now containing the spin crossover molecules inside. And this is what happens when we measure the current across the carbon nanotube, okay? As a function of the temperature. So we start at room temperature, we cool down our sample, and then we see that when we reach to the spin crossover transition temperature, there is a jump to a higher current state, and then it continues decreasing. So it looks like the current is detecting this spin crossover switch in the molecule. So the current on the nanotube is detecting the spin crossover switch. If we now continue increasing the temperature, what we see is that there is a tiny jump here, but actually current continues to be in this high conductance state until at around 225 Kelvin, it decays again to the low conductance state. And we see this in many of the samples. This, I think, is around 35%, what for us is quite big, actually. So what this looks like is happening here is that the current in the carbon nanotube is sensitive to the spin crossover transition. That's why we are here in this high spin state. When it switches to the low spin state, we have a switch to a different state. But what is very strange for us is that we have this thermal hysteresis. The crystals of the molecules do not have thermal hysteresis, okay? Well, we could fit this with a thermally activated model with an Arrhenius law, and we see that this switch seems to be related to a really strong drop of the activation energy for transport across the carbon nanotube. This is actually something that has been seen before in measurements taken directly across the crystals, okay? So in this kind of crystals, they were putting some probes on top of the crystal, and you can see that they were seeing very similar hysteresis loops to what we see. I have to highlight that in this case, the hysteresis is there intrinsically to the molecule, so they can see it in the magnetism of the molecules. This is not our case. So in our case, the hysteresis is opening. But we had this very recent report on 2019 that showed that by creating films, very thin films of these spin crossover molecules, where you don't have a hysteresis when it's large enough, by making smaller the thickness of the film down to the 300 nanometers, you start to open some hysteresis cycles. So I think this is what is precisely happening in our carbon nanotube, with the difference that in our case is much more confined. Okay. So we were also wondering what could be the origin of this opening of the hysteresis, but also of these different conductance between high spin and low spin. We think that this could be of a mechanical origin. So the low spin molecules are smaller than the high ones, the high spin ones. So this could induce different strain on the carbon nanotubes. It could be as well a magnetic origin, because the spin 2 may be inducing some kind of Lorentz scattering on the tube that we don't have with the spin 0. We don't know, but we don't think is this case. And also it could be an electrostatical origin, because it is also well known that when the molecule changes the volume, also is changing the electrical electron charge distribution in the molecule, so that the effective dipole moment is changing in the molecule. So this could be coupling to the to the carbon nanotube, for example, through a local gating effect, or through the interaction with the phonons, and as they have described for graphene in this paper here. Okay, so to try to understand a bit more what is our situation, what we actually did in collaboration with, she did, Carmen Calzado at the University of Sevilla, she modeled our systems. She put the molecule inside the nanotube, and she studied what is the most stable situation. The first thing she sees is that the molecule prefers to be in the central part of the nanotube and not really in contact to the wall. But apart from that, there are several configurations in which the molecule feels more comfortable with not so much energy difference. The relevant thing for us is that when she calculates the relative energy between high spin and low spin state, what she gets is that in general is higher than when the molecule is isolated or in crystals. So this would in general tend to push the critical temperature to higher temperatures. In this direction, even more relevant is that the interaction energy, she finds that the interaction is much stronger between molecule and nanotube when the molecule is in the low spin state. Okay, this would explain the opening of our hysteresis loop. Okay, so once the molecule moves from high spin to low spin, it prefers to stay there than going back to the high spin. That's why this second transition is most likely moved to higher temperatures. They have also calculated the density of states and the density of states projected on the carbon nanotube, and they see how indeed is actually different for the low spin and the high spin state around the Fermi level. So if they calculate now this the conductance as a function of the temperature, they see more or less what we see, that the high conductance, the high spin state and the low spin state produced a different conductance in the carbon nanotube. They see actually the opposite. They see that the high spin is conducting more than the low spin state. We thought that this could be maybe just because our system is not ideal, so we had some defects or some I don't know, it's not really ideal, it's not like their calculations. But actually we found out that if they move the Fermi level to more negative values, you can actually reverse the situation and get into our scenario. Unfortunately, we didn't do measurements with gate, but we can actually have this situation because we know that our carbon nanotubes are p-doped and sometimes even heavily p-doped. And the effect could be similar to moving the Fermi level. Okay. Our system is also subject to a strong electrical field, so they have also tried to see what happens to the high spin and low spin state when you apply an electrical field. And it's not simple because it depends on the orientation of the electrical field, but just to show you that we could further stabilize or destabilize the high spin to low spin transition. We didn't do much measurements as a function of the bias, but we do have some at lower bias where we have this kind of situation now. We don't have a hysteresis, and what we observe when we cool down is that there is a spin transition, so a conductance transition around the spin crossover transition, but then it's not always all the time in what it would be the low spin state, but it is actually switching back and forth between what it would be the low spin and the high spin state. Still is most of the time on the low spin state, like almost more than 4 times, but this indicates that indeed the bias may have a role in stabilizing or destabilizing the spin states of the molecule. Okay, so with this, now I would like just to briefly, well, I hope with this part you could see how we are actually able to fabricate this kind of hybrid systems that are very interesting for Spintronics, that we can use the mechanical effect of nanotube, but also the electrical field to modulate a bit the properties of the molecules. And if I have just a couple of minutes only, I would like to show you just also what we have done with some 2D magnetic heterostructures. So the idea here is also to use the magnetic part of these systems and also to put them in these superconducting resonators to try to have a strong coupling to the spin and to use them as qubits. But for that, we were wondering what happens if instead of using the molecules, we use other low-dimensional materials that also have this spin. So for that, in collaboration with Andres Castellanos and Mar Garcia at the ICMM, we have studied this material, the Cylindric. Okay. The nice thing is that this is a layered heterostructure that can be exfoliated and that has a 3% of iron atoms in the lattice. So we could be using those iron atoms as well, potential qubits. Well, the reason why this material is called Cylindric, I think, is quite obvious, right? Because it crystallizes in these cylinders. Here in these images, you can see also that is a layered heterostructure. So what we have basically done is to exfoliate these materials using a liquid phase exfoliation. This Lucia did. Basically, she grinds the material, she disperses the material in a solution, and by a series of processes of ultrasonication, centrifugation, and filtering, we are able to get a very thin flakes. Actually, we are able to go to the monolayer of this material. This is quite an aggressive process, so before using them, we have checked that indeed the crystallinity is preserved. The presence of iron in the flakes is also preserved, what is important. And what we see, I'm not going to go into detail because my time is running up, but also we see the magnetic interactions of the iron in the lattice of the cylinder. Okay, so the idea now would be to move these flakes into the same resonator that I was showing you before. We have done that already by the electrophoresis. So now we would like to study from a fundamental perspective how or what is the information that we can obtain between the interaction of the photon with these magnetic centers. Okay, so well, with this I actually finish. My take-home message is actually quite simple. I hope you could see, or I was able to show how we can create these heterostructures with improved properties that may allow us to use molecules into this world of the quantum resonators. And of course, I would like to finish acknowledging all the people that have worked on this. Aise and Lucia, that did most of the fabrication and electron transport characterization. Emilio, Julia, Jose did most of the synthesis. Marina, Arturo, and Alicia helped with the microwave measurements and part of the fabrication. The people in the ICMM, as I said, for the 2D materials. The people in the University of Sevilla for calculations, and Fernando that started with the whole idea of reducing this constriction and trying to get higher spin photon couplings. Okay, so thank you for your attention.
Okay, thank you very much, Enrique, for this wonderful talk and this fascinating insight to what you can do with single molecules and how you can put them as a ring around nanotubes. This is sounds amazing.
Thank you.
So I would say that the talk is now open for questions or for discussions. So please, whoever would like to ask a question, I will be unmuted. Actually, I can do that for all. Okay, so let me start with a question from somebody who, I mean, my background is a bit more superconducting and semiconducting qubits. And I wonder how the interaction could be between, say, these traditional or more traditional solid state qubits and these molecules. Is there any future direction to be seen already now?
Well, actually, some of the things that have been proposed actually is to make this kind of hybrid systems where actually you could get in the same, for example, transmission line, you could try to implement this kind of molecular qubits with other more traditional, as you said, maybe qubits based on superconducting or semiconducting materials, and try to a bit use the advantages that both kind of qubits may have. For example, maybe try to use molecules for something related to logic gates, but try to use the superconducting qubits for more the storage of the information. And so yeah, so actually I don't think one is exclusive from the others. I would say that we could try to use all of them to build more complex architectures based on them.
And you mentioned that in one molecule you may support several qubits. How many roughly?
So I think that depends on, so if I go here to the first part of the presentation, so in the end what you need is a magnetic spectrum of a molecule that is giving you, let me go, is somewhere here. So basically what you need to do is to have a magnetic spectrum that is giving you, for a specific magnetic field, for example, that is giving you energy spacing between the levels that are different. Okay, so that when you apply a microwave photon with a specific frequency, you are addressing just one of them. Okay, so let's say that you could build much more complexes, that much more complex molecules that could have much more complex magnetic spectra. so that I don't know where is the limit basically. So I guess that you can really get monsters, so to say, that can have really a large number of qubits. But the basic idea is this, yeah, so that you can have, for example, for a specific field, you can have energy spaces that are all different from each other, so that you address just one of the qubits and you are not addressing all at the same time. What would ruin, of course, the idea. I don't know if that was clear.
Okay. So more questions.
Yeah, maybe I have a question, if I may, Simon.
Yeah, please, you can unmute yourself.
Yeah. So, Enrique, for the last part, for these 2D materials, how do you actually implement a qubit there? I missed this part.
No, yeah. So this is not really actually more in the qubit. So in here we are actually, maybe I was not clear. So the idea here would be actually to more study the fundamental properties of what kind of information we can get from the interaction between the photon and this magnetic part. The way to implement a qubit in these materials, well, most likely you will need something else that is not iron, but in the end, if you can have a material like this in here, where you have very few magnetic parts with, let's say, spin 1/2, that would be a very similar idea to a spin in a molecule in the end. Here you probably don't have anisotropy, but you can always make the splitting with a magnetic field, for example, so that again you can have these two states that we can use for a qubit. But for now, we are just thinking on just seeing what happens, or on just seeing how this photon can interact with this magnetic part. The idea of this 2D material actually is that with this kind of geometry, you would be passing the current, or so the superconducting current would be passing directly through the material. So also would be in very close contact to the magnetic center. So we are just interested in see what can happen in this situation.
Yeah, and related to the geometry, could you use maybe this 2D material to create like a weak link in a Josephson junction and use this just directly as a, transmon-like qubit?
Yeah, that is also an option. Actually, of course, the qubit that we want to have actually does not need to be purely the molecule or purely these magnetic atoms. It could be something hybridized with a more complex system. For example, a junction, as you were saying, that maybe is coupled to the spin, for example, or just the junction itself. Yeah. So we are thinking on many different geometries here. For example, we could also try to use these materials in particular in heterostructures with superconducting devices, so that we don't really break the transmission line. That is quite a problem actually, but still it's in very close contact to the central line, our magnetic part.
Yeah, I see. Yeah,
or we could just build a weak link here. Yeah.
Okay, thank you.
May I have one more? When you in the very beginning you mentioned that you can tune the coherence or the T2 time of your system. How are you doing that? Can you reduce the coupling, or is it somehow the spectral density of the environment what you tune?
Well, here, as far as I know, what chemists are trying to do here is, on the one hand, they are trying to do this organic stuff that prevent the spin interacting with something else on the environment. And also what they are trying to do is to, for example, reduce the number of nuclear spins that may be around around our central part, around the spin that we want to use as a qubit. In the end, the idea would be to reduce any kind of interactions that we may have with any other magnetic component in our system. Okay, but yeah, those would be the basic, I would say. So bigger organic cells based on materials that don't have a nuclear spin.
Okay. Further questions? So if not, we close officially, and those who want to stay to chat a little are welcome to do so. Okay, so thanks again to Enrique, and thanks for your attention. So
Thank you.
bye.